Today, we are diving into a huge breakthrough in cryptographic proofs. It's something that promises a massive, and I mean massive, leap in performance by thinking in the simplest terms you can imagine, just zeros and ones. It's a system that goes right back to the very basics of how computers work to unlock some seriously incredible speed.
It sounds a little backward, doesn't it? But it turns out this revolutionary new approach proves that to go a whole lot faster, we need to speak the computer's most fundamental language.
All right, so before we can really appreciate this new system, we've got to get our heads around the magic it's built on. Zero-knowledge proofs, or ZPs. It's a concept that sounds like something straight out of science fiction, but it's very, very real and unbelievably powerful.
So here's the crucial idea. I can prove to you that I know a secret without telling you the secret itself. Just let that sink in for a second. Proving you know something without revealing a single bit of that knowledge. Now, in the world of computing, that secret could be anything, a password, or even the fact that a super complex financial transaction was done correctly. So how is that even possible? Well, there's a classic analogy that makes it all click.
This is the famous cave analogy. Okay, picture this. You enter a circular cave that has two paths. Let's call them A and B. Deep inside, they're connected by a locked secret door. Now, your friend waits outside. You go down one of the paths, say path B. Then your friend, who has no idea which way you went, randomly shouts, "Come out of path A." Well, if you were already in A, that'd be easy, but you're in B. So you use your secret, the key to the door, to cross over and pop out of path A, just like they asked. You do this over and over again. Every single time, you emerge from the correct path. Pretty soon, your friend becomes totally convinced you have the key, but they never see the key, they never see the door, they learn nothing about the secret itself. That is a zero-knowledge proof.
Now, this kind of cryptographic magic is an absolute game changer for things like blockchain scaling and privacy. But, of course, there's a catch, and it is a big one. Performing this trick is incredibly, ridiculously expensive. You know, generating these proofs is like trying to run a massive, clunky old engine. It just eats up enormous amounts of computational power, which makes it slow and costly. And honestly, this has been the single biggest wall standing in the way of using them everywhere.
And it's not just one specific problem either. The world of ZKPs has all these different flavors, like ZK snarks and ZK starks. And they each have their own trade-offs, right? Snarks give you these tiny little proofs, but they need what's called a trusted setup, which is complicated. Starks are kind of the opposite. But here's the thing. No matter which one you pick, they all wrestle with that same fundamental issue. They are computationally intense.
This quote from the CySIC team really just hits the nail on the head. The proof generation process is the bottleneck. It's the mountain that pretty much everyone in this space is trying to figure out how to climb faster.
And that brings us to the hero of our story today. A brand new system championed by none other than Ethereum co-founder Vitalik Buterin that completely rethinks the problem from the ground up. And its name is Binius.
Vitalik himself describes it as a system for highly efficient proofs over binary fields. And you got to focus on those last two words, binary fields, because that is the key to everything.
Okay, so this is the big aha moment. See, traditional proof systems, they basically force every problem into a mathematical box that isn't really a natural fit. They work with these enormous 256-bit numbers. But think about it. Most computer operations, like a simple on-off switch or a true-false flag, that's just a single bit, a 0 or a 1. Using a massive number for that is like using a giant shipping container to mail a single letter. It's total overkill. So, Binius completely flips the script. Instead of forcing the problem to fit the math, it adapts the math to fit the problem. It works directly with the bits themselves.
So how on earth does it do this? This is where it gets really, really cool. Binius fundamentally reorganizes the data it's proving using a pretty wild structure called a hypercube. So instead of seeing data as just a flat line of numbers, one after another, Binius structures it as a multidimensional grid, made up of individual bits. Let's try to picture what that actually means.
Okay, let's build this up. You start with one dimension, just a simple line of bits. Now, add a second dimension, and you get a square grid of bits. Add a third dimension, and now you've got a cube of bits. Now try to imagine adding a fourth dimension, a fifth, a sixth. You can't really draw it in your head, but mathematically, you've just created a hypercube of bits. And this data structure is the absolute heart of how Binius works.
And this structure is the whole secret.
Because the data is organized this way, Binius can use a very specific and extremely efficient type of math called binary finite field arithmetic. It's basically a system of logic that's designed specifically to work with just zeros and ones, which makes it lightning fast on this kind of grid structure.
Okay, so we've got bits, and we've got this hypercube thing. But where does the massive speed boost actually come from? Well, the answer is just beautifully simple. It comes from finally speaking the computer's native language.
Let's break down exactly why this is so much faster. First, computers think in binary. It's their native tongue. By operating directly in binary, Binius is working in perfect harmony with the CPU's fundamental design. There's no translation needed. This gets rid of all that waste we talked about. You're not using these giant data types for tiny little pieces of information anymore. It's this perfect alignment between the math and the physical hardware, this hardware harmony, that unlocks such an incredible performance boost.
So what does this all mean for the future? Well, it means we're on the cusp of a major leap forward in what we can prove and how quickly we can prove it.
The big takeaway is this: Binius and innovations like it are absolutely demolishing the walls of cost and time that have held ZKPs back for so long. They are finally making the dream of verifiable computation, the ability to prove that any program was run correctly, a practical, everyday reality.
And that leaves us with a really fascinating final thought. Imagine a world where you don't have to trust that some complex calculation was done right, you just receive a tiny instant proof that it was. I mean, from secure voting to cloud computing to decentralized AI, the possibilities are just staggering. So if proving something becomes cheap and instant, what will we choose to build?